Welcome to the Problems Channel Season 3, Episode 6, the episode which I titled Triangular Spring Oscillator, because in this episode we will solve a problem in which we will recover the cyclic frequency of a simple harmonic oscillator that has the shape of an equilateral triangle. But before we deep dive into the underlying physics and mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you and use the comment section in that episode, and I will do my best to answer all of your questions. In the physics problem S3P1, we're given three particles or 3 point masses, three small beads or three small balls that are positioned at the vertices of an equilateral triangle as shown over here, and all these three particles are connected pairwise with three identical ideal springs as shown in the diagram over here on the left side of your screen. And we're told that all three particles have one and the same mass m, and all three ideal springs have one and the same constant k, and k. We assume that the system is, let's say, positioned in the horizontal plane, and at some point all three masses, all 3 points that form an equilateral triangle, are pulled by exactly the same amount, let's say, away from the center of an equilateral triangle, and then they are let go. As the result of this uniform radial pull and let go maneuver, the system, the 3 point masses and the three ideal springs begin executing what is known as simple harmonic oscillation in the horizontal plane and without friction. The objective of this problem is to recover the cyclic frequency omega, or let's say omega 0, because this will be a constant, omega 0 of the triangular spring oscillator as that system oscillates as a whole. And this problem can be solved in at least three different ways, and we will discuss all these three ways in this particular order. We will start with the middle school solution of this problem that is based on the Newtonian formalism. We'll use the Newton's second law. Then we will discuss the solution of this problem that is based on the idea of conservation of total mechanical energy. And in the third and final discussion of this episode, we will look at how this problem can be solved using the Lagrange and formalism. Before you take on the solution of this problem from the Newtonian formalism standpoint, it pays to know at least two things. First, it is a good idea to solve a similar problem that is based on a single or a traditional or a linear harmonic oscillator in which there involved is only one string to the end of which, let's say, is attached a point mass. That's number one, and you should be comfortable with the solution of that problem. And second thing that is helpful during the solution of this problem is the basic fact about regular polygons, which amounts to the following. Recall that, let's pretend that on the right hand side of your screen, I portrayed a regular polygon on N, where N is evidently greater than 2 vertices. And from the study of plain Euclidean geometry, we remember that every such regular polygon on N greater than 2 vertices possesses a unique circumcircle and a unique circumcenter, which is basically the center of a circle into which the regular polygon at hand is inscribed. I showed the circle over here in white, and the same regular polygon on N greater than 2 vertices possesses a unique incircle with a unique incenter, or basically a circle which is inscribed into the parent regular polygon. Now, in this case, in the case of a regular polygon on N vertices, the incenter and the circumcenter are one and the same point, and to that point we refer as the center, shown over here in green, the center of that regular polygon. That center plays actually an important role in the study of rigid symmetries of that geometric shape and the theory of groups, because the congruence rotations of that regular polygon precisely about that center of the polygon in the parent plane under the operation of composition form a finite cyclic commutative group, which also happens to be a subgroup of the group of all rigid symmetries of a regular polygon, which is formed by what? By the rotations precisely about the center of the polygon in the parent plane, the congruence rotations, and the reflections of that polygon with respect to its axis of symmetry. But this is a slightly higher mathematics that I don't really see how we can use it over here. Maybe we can work it in somehow, but the fact that we will need in this problem is the following. The complete angle that we can, for example, form as follows. If we stand in the center of a regular polygon shown over here, and it doesn't really matter, but let's say we look at this here vertex of that regular polygon, then if we make one complete revolution by looking at all the vertices of the parent regular polygon in either direction, it doesn't really matter, in the positive or counterclockwise or negative clockwise direction, then what is the magnitude of the angle that we will traverse? Well, it should be evident that the magnitude of that angle will be 2 pi radians, or the complete revolution or full rotation angle. And with regular polygons, with all non-degenerate regular polygons on N greater than 2 vertices, that complete full rotation angle of 2 pi radians is divided uniformly into how many? Precisely into N by the number of vertices central angles, all of which are originated or have their vertex at the center of the regular polygon, and all such angles subtend the circular arcs, the arcs of the corresponding circumcircle that is delineated by the corresponding two immediately adjacent vertices of that regular polygon. So that means that the magnitude of one central angle in the regular polygon is what? It will be 2 pi divided by n, and all these central angles will also participate in the formation of how many? Exactly n triangles, each of which will be what? Isosceles. Why? Because the sides of all these triangles are precisely the radii of the corresponding circumcircle of the parent regular polygon on n vertices, and by two propositions, book 1 proposition 32, From Euclid's elements, we know that the magnitudes of all the interior angles of any non-degenerate planar Euclidean triangle sum to what? Sum to 2 right angles or 2 pi radians. And by Euclid's Elements, Book 1, Proposition 5, the famous Pons Asinorum, we know that the magnitudes of the interior angles at the base of every non-degenerate Euclidean plane isosceles triangle are what? They are equal by magnitude, so these magnitudes are equal. So if we designate these angles with x, then what we will have? We will have 2 pi over n plus 2x sum to pi radians. And solving this equation for x, what do we have? We have 2x equal to pi. We can move 2 pi over n to the right hand side of this equal sign, factor pi out, and we'll have what? 1 minus 2 over n, which is to say that 2x is equal to n minus 2 over n scaled by pi, and then that means that x, the magnitude of these angles in all n corresponding isosceles triangles formed as shown as I explained, will be equal to what? It will be n minus 2 over 2n times pi. Remember this result because we will come back to that result in a moment. And now we want to analyze what kind of forces make our each and every point mass in our process oscillate, and how do these forces come to be. Before we can understand how the forces that make our point masses oscillate come to be, we should really study the behavior of the springs themselves that make up our system. To that end, let us assume for a moment that in its neutral state, or in the state of stable equilibrium, the size of each ideal spring that connects all three of our point masses is L0 as depicted over here. The distance between each point mass is L0 in the state of steady equilibrium. Now let's say for a moment, let's assume now next that the point masses were radially displaced from that state of steady equilibrium. My drawing is here horribly out of scale and out of shape, but the important thing to understand over here that, for example, in the expanded state, when with respect to the state of steady equilibrium, the point masses are radially displaced outward, as shown over here in red. Then let us assume again for a moment that the length of the expanded string shown over here is L. Then what can we say about the change in the length of the spring in the expanded state with respect to the length of the string in its neutral or steady equilibrium state? Why do we want to know this change? Well, we want to know this change because we know that in the case of a traditional, let's say, linear or single spring oscillator, the change in the relatively small or small enough change in the length of that spring generates precisely the so-called restoring or elastic, or sometimes it is called pseudo-elastic force, and that force is what drives the oscillating behavior of the point mass. So in this case, what can we do? Well, in this case, we can project the length of the neutral state spring that connects all our three masses orthogonally onto the spring that is expanded as shown over here. In this case, we simply project this point mass onto the, in this case, horizontal line L orthogonally as shown with the right angle here. We do this the same thing for that point mass, project over here. So this length over here, maybe I can even use green so you guys can see better. This length over here is precisely L0 is the same length, and evidently due to the symmetry, because we're dealing with a regular polygon on n equal to 3, an equilateral triangle on three vertices, that situation will hold for all three, for all the other remaining springs. For example, if we do the same thing for this side, it will look like this, and for this side it will look like that. We will have exactly the same situation for all three expanded springs, and due to the symmetry of this system, we pick one such spring, because even one spring in this case is a faithful representative for the entire set of all 3, 4, 5, or 17 springs, and if we have a regular 17 gun, let's say. So in this case, the length of the expanded spring, or each extended ideal spring, can be represented which way? Well, these little segments over here that I showed were designated with lambda here and here, also participate in the formation of this length L. In other words, we treat L as a composite quantity that is put together with three line segments, lambda plus L0 plus another lambda. That comes down to 2 lambda plus L0. Would you agree this is nothing? In fancy highbrow mathematical terms, we will say that these three line segments partition or tile the length L tight with no gaps and no overlaps, but the simple geometry of this expanded string works out that way. And then what do we have? Let's take a look at this. We now have L is equal to 2 lambda plus L0, and from here it follows what? That for delta L, which is computed as the difference between L and L0 minus L0, from this relation we instantly have 2 lambda. It is that straightforward, and it is these two little chunks over here, the lambda shown on the left and lambda shown on the right, is what represents the expansion of the string with respect to the neutral state in which every ideal spring has length L0. And I will not be redrawing this diagram that I show over here, guys. You should be able to see it in your mind's eye. Let's say this is our mass M, and M over here. We understand what's going on. So here we underwent an expansion. This expansion is radial. We expanded our strings with respect to the center of the regular polygon, which we discussed in the previous segment. So the expansion went outward this way. So this expansion generated this change in the length of the spring that was not expanded in the steady equilibrium state. And in your mind's eye, what I suggest you guys do is flip this situation around. Let's say, assume for a moment, see it in your mind's eye, that the outer equilateral triangle shown as red represents a neutral state, or the state of steady equilibrium in this case, because harmonic oscillation is basically small amplitudes or small enough amplitude motions around the state of or point of stable equilibrium. So let's say this outer equilateral triangle shown in red represents that state of equilibrium, neutral state, and the smaller triangle inside represents the compressed system, where the length of each ideal spring that forms our system is compressed. So now what would this over here relation look like? Well, exactly the same thing, except of assembling the length L as a composite quantity from the respective pieces. We will do the same thing for the length L0. So this is now L0, and this is a smaller string. So we will write pretty much the same thing. We will say that L0 is equal to lambda plus L, because this now is not L0 but L. Less lambda, so it comes out to 2 lambda plus L. And from that relation, what will we say? We'll say that delta L in this case, which is still L minus L0, L minus L0, 2 lambda moves to the left-hand side of the equal sign. It will be minus 2 lambda. And that negative sign over here mathematically reflects which physical phenomenon? Exactly, this mathematical material represents the fact that in physics the length of the original spring, ideal spring that connects these 2 point masses, contracted or became smaller in plain English. That's all there is to it. So by its absolute value, the change in the length of all ideal springs that make up our system will be one and the same. It will be 2 lambda. So now that we understand how this magnitude came to be, this is actually nothing more than, again, really middle school geometry. This is nothing complicated over here. But now we go back to, remember, I told you guys that if you taking on this problem, then you should be at home with a problem where, let's say, we have somehow ideal spring with the point mass attached to it. At this point, we will say our x equal to 0. Let's say we place the coordinate system this way, and in this narrow band over here, somehow our point oscillates back and forth with respect to the point of stable equilibrium. Then every time the point mass deviates in either direction, it is this deviation generates or let's say it's a small intended pun, what springs into action. What springs into action is the elastic force that is generated by that spring, and that force is restoring because it wants to bring the misbehaving point mass m back into that state of stable equilibrium. And what is the expression for that force? For that force, technically we will write it with the negative sign, k times delta L, and the negative sign over here exactly captures the fact that this force is restoring. For example, when x over here, we will here in this respect we will write it as follows, minus kx. So this way, when x is greater than zero, then this force is what? Is also negative. It wants to bring it back. And if x is less than 0, in other words, if the point that oscillates finds itself on this side, so x is less than 0, then this force will be positive. It will try to push that point back into that point in that corresponds to the stable equilibrium of the system. And this is basically, fundamentally, ideally, that's the fact that you guys were supposed to deduce on your own. This is the, so to speak, the driving force behind the origin of what makes our all 3 point masses oscillate. And remember that this force shown over here, minus k delta L, where k is the spring constant of each ideal spring that forms our system, k over here. That force is generated by how many springs? That force is generated by one sample spring, for example, this one. this spring. And now we will look at how does this force F, how is this force directed, and actually how many forces make our single point mass, for example, this one or this one or this one, how many forces act on our point mass. Awesome. I took the time to erase the board on the left side of your screen, prepare it for the upcoming segment. And here on top, I wrote the result that we deduced in the previous segment by value. And usually I don't want to be, and in physics, we do not really like to be that picky. We can use F without the vertical bars, but by magnitude, not by direction, but by magnitude, our force is equal to K delta L. We explained where delta L came from, which is 2 times K times lambda. Lambda is this little segment over here, little chunk that's left on the length of the expanded ideal spring when the non-expanded or the neutral state ideal spring is orthogonally projected on the expanded string. We understand where that came from. And now we want to understand how many forces act on each and every individual point mass shown over here. And from that point, we will be able to make progress. So here it should be evident that because each massive point is connected with two springs, two ideal springs with its immediate neighbor, exactly two elastic or restoring or pseudo-elastic forces act on that point. And that will be the case no matter how many vertices we have in our regular polygon. In this somewhat toy problem, we have a regular polygon on 3 vertices or an equilateral triangle, but imagine that we have a spring oscillator that has the shape not of an equilateral triangle but of a square, or the shape of a regular pentagon, or the shape of a regular hexagon, and so on. Still, this will be the case. Each and every point mass only sees, let's say, from its immediate neighbor standpoint, exactly two neighbors, one on one side, one on the other. If we look inside into the proverbial center of the regular polygon, each such point mass will see exactly one neighbor on its right, immediate neighbor, and one immediate neighbor on its left. And these directions are occupied by the ideal springs. The elastic force that is generated in these springs as the springs expand and contract is precisely what drives the simple harmonic oscillation of these points. And now, basically, that is to say that one force, let me use maybe green, one elastic force acts this way. This is one force. And the other force acts, let's say, this way. This is another elastic force. You see, this force and this force. Now, what can we say about we know that the directions of these specific elastic forces that are generated by the oscillating springs always coincide with the spring itself, with the straight line that goes through the string. So this force direction-wise points this way, acts along this spring, and this force acts along that spring. We know the directions are different, but what can we say about the magnitude? The magnitude of each force is the same. So the magnitude, let's say, of this force and the magnitude of this force are one and the same. So on my drawing, it probably doesn't look that way, but if you draw a circle centered at the point M, and the circle that has a radius that is equal to the magnitude of one force, we have to hit the other. So this force will be this, that much in magnitude, and this one is that much in magnitude. And what does that mean? Well, we now go back to our Newtonian formalism, and the second law of motion due to Newton, which is the part of the Newtonian formalism, states what? The net force that acts on a given point mass is what generates the proverbial ma, mass times acceleration. Now, how do we find the net force in this case? Well, one way to find the net force is we can use either the so-called triangle rule or the parallelogram rule. I guess in this case it's easier because the forces originated one at the same point. It is easier to let's say use the parallelogram law. So let's say we have two forces, force number one and force number two, both restoring forces. They're equal in magnitude. We know that the magnitude is the same. The directions is known. What is the angle? What is this angle between these forces? Well, we already deduced that angle in our previous, in the very first segment that we started working with, because if we carefully draw this radius of the corresponding circumcircle of the corresponding parent regular polygon or an equilateral triangle in this case, then the angle between the elastic forces F and F, the ones that make our, for example, this point again oscillate in a simple harmonic fashion, this angle is formed by what? By two smaller angles whose magnitude we already deduced. This angle, remember, is n minus 2 over n pi, not divided by 2n, because the division by 2 is given by here for the smaller angle, but two of these angles put together, the magnitude of the angle will be n minus 2 divided by n times pi. So now we construct a straight line that is parallel to this vector. Is it? Probably not. I apologize if it's not. Then we construct another straight line that is parallel to this vector. We obtain the point which will be the terminal point of the sum of these two vectors. I will depict that vector with red. This will be the sum total. I will designate it with F net. And if, let's say, the length of this side of our parallelogram is equal to the length of this side, then in book one, I forgot which specific proposition, Euclid proves what, that the opposite sides in any non-degenerate parallelogram must equal one another. But in our case, both original sides that generated this parallelogram are equal in length. So this side must be equal to this one, and then this side must be equal to this one. So we now have a parallelogram in which the length of all four of its sides are what? One and the same. There is a special name for this parallelogram. It's called a rhombus. And if in any arbitrary parallelogram, that is in general not the case, in a rhombus, in the specific case, in the case of a rhombus, actually any diagonal of a rhombus does what? It cuts the interior angle of the parent rhombus in precisely half. That means that in our case, the magnitude of this angle must be equal to the magnitude of this angle. And what is this angle over here? What is the magnitude of this angle? Well, we already deduced it, n minus 2 over 2n times pi. And that means that the net force that acts on each and every point mass in our case acts precisely in the radial direction. And if in the previous segments you guys were not clear, what is Roman talking about? Radial direction, radial displacement. What is radial? Radial means precisely along a radius of the corresponding circumcircle of the parent regular polygon and n vertices, or of the parent equilateral triangle. So the net force in this case will act along the line that passes through the oscillating point itself and what? And the circumcenter of the parent equilateral triangle. Oh, it will act in this direction. Which color did I use? Red. So let's designate this with, let's say, this will be a dashed line shown in red, but the net force of between the sum of the vector sum of these two guys will act precisely in this direction, will point in this direction, precisely because of these angles over here. You see, these angles are equal. We computed the magnitude. This is that magnitude, and now we understand that each point will oscillate in the radial direction. So we can say that each point mass in our case, this one, and this one, oscillates or executes a radial motion. And what is the definition of a motion that is radial? Well, in this case, it's my term. Feel free to invent a better one. The radial means simply along a corresponding radius of the circumcenter of the parent regular polygon on n vertices, or in this case, the circumcenter of an equilateral triangle. So this point will also be acted on by the net force shown over here. It will precisely pass through the point O, and this point will be acted on by the net force that points this way and passes precisely through the point. So this force will be F net, and this force over here will be F net. So these three forces act on each one of the point masses, and these are the forces that generate the corresponding harmonic oscillation of each point. This one, and this one. And now the final question is, we remember that how many parameters in this problem we're given? We're only given two parameters. K, the spring constant of each ideal spring, and mass m. We're not given L, we're not given L0, we're not given lambda. This is all auxiliary material that helps us develop a solution of the problem, but none of this material is given to us. So what are we to do? Well, we should try, now that we understand that the net force that drives or that explains the simple harmonic oscillation of each point is radial in its direction, we understand that each point mass, this one is this one, these points act along the corresponding radius of the parent circumcircle of a regular polygon or over an equilateral triangle. And what do we want to do? Well, now we want to tie somehow this delta L or lambda into this radial directions. And in this respect, what can we say? Well, we can introduce exactly the same thing. Let's use the green one. We can designate R0. Look at this. R0 is the radius of the circumcircle of our regular polygon on n vertices, or of an equilateral triangle in the neutral state, in the state of stable equilibrium. I will not be making more mess over here, but you guys understand this circle will run somehow this way. And then we can introduce as R the current value, R this way. So this right here will be R. From here to here, this will be R. As the radius of the circumcircle that is generated by the expanded, let's say expanded triangle, this circle will run this way. And now we can tie the material in terms of R, R0 and R, to the material that we have expressed in terms of delta L and lambda. And that connection is very straightforward. And we are almost done if we realize that we can tie the change in the radial direction of each oscillating point mass with its change in the length of the actual physical ideal spring that each point mass is connected with its immediate neighbors as follows. Let's look at this. From this triangle over here, this, and this, what can we say? What is the expression for lambda? Well, 1 lambda is equal to 1 lambda is equal to delta r, our delta r, which is, I'll tell you in a second what it is, times the cosine of this angle, and the cosine of this angle we already deduced in the previous segments. This is our thing. And what is delta r? Delta r is simply r minus r0, you see? R minus r0. R minus r0. That's it. It's that straightforward. From this triangle, you should be able to deduce that this is delta r times the cosine of this angle equal to lambda. From here, it follows that for 2 lambda, let's say for 2 lambda, we have 2 times delta r times the cosine of the angle n minus 2 over 2n pi. And once this is on the books, what can we say about the magnitude of the net force? The magnitude of the net force also should be straightforward. You guys should be able to write it down before even I do. What is this? How did we obtain this net force over here? The direction we established, but we added this vector to this vector, and this right here will be what? Now this triangle will be what? Isosceles. By magnitude, the length of this side is f, the length of this side is f. We project any one of these sides onto the base of this isosceles triangle, the length of whose base represents precisely the magnitude of the net force. And what is this? Well, it will be 2 times absolute value of each individual elastic force times the cosine of the same angle, n minus 2 over 2n pi. And what is f? Well, it is this guy. So it is, if we multiply this by k, then we will have precisely the force f. So in terms of all the materials that we have, what will we have? 2 times, what is f? Well, it's 2 times delta r times the cosine of n minus 2 over 2n pi times this cosine. So what do we have? Square, and multiplied by what? Because in f we have k times k. And if we rewrite this expression, now that we understand where it came from, as follows. We can rewrite it as follows. 4 cosine squared of n minus 2 over 2n pi times k times delta r. Then what is this? What does this magnitude represent? That magnitude represents precisely the spring constant of a virtual spring. If we imagine that this spring, instead of the physical spring that connects this, let's say, point mass with its immediate neighbors, this virtual spring runs from that point, and it's connected precisely to the circumcenter of the parent equilateral triangle. In other words, the net force mathematically, purely mathematically, can be modeled with a virtual string which is attached to the circumcenter of the parent equilateral triangle and runs this way, connects this point, and this is the constant of this virtual spring. And now let me take a short break, erase this material, and make the results that we obtained so far more readable for your convenience, guys. Awesome. In the previous segment, we deduced that the magnitude of the net force, or we can say the magnitude of the virtual restoring or the virtual elastic force that acts radially and generates the simple harmonic oscillation of each and every point mass that we have in this problem can be expressed in terms of the material that is baked into each individual restoring force or genuine restoring force that is generated by the physical ideal spring that is attached to each point mass, has this shape over here where K prime, with K prime I designated the spring of this with K prime I designated the constant, the constant of the virtual spring that runs radially and is attached to the circumcenter of the parent equilateral triangle. Can be expressed this way: 4 cosine square of n minus 2 over 2n scaled by pi times k, and k in this case is the constant of the actual physical strength. So this is, remember that we studied the idea, I even branched out the whole dedicated study of this material into the problem-solving approach called mathematical equivalence. From the big scope of things, we studied it at the end of the season 2, and now we see it on a somewhat miniature scale, but still it doesn't really matter. Mathematically, if we can make the shape of some object mathematically look exactly the same as the shape of a known object, then this similar object can be modeled or is a faithful model of the original object. And in this case, this force is a faithful model of a restoring force that is generated not by a physical spring, each of the two physical springs, by a virtual spring attached to the circumcenter of the parent equilateral triangle. This is the constant of that virtual spring. And pretty much if you are in middle school, you most likely do not know anything about differential equations, and then you will have to take basically on faith the idea that the grown-ups or your teacher in the classroom will tell you that the value of the cyclic frequency of this oscillation in this case was simply given to you. It's not deduced, it will be simply given to you as K prime over M. This is how this thing work out, but in slightly more for much more advanced, let's say high school students who know something or have heard about differential equations. And if you are in college, then you definitely have to know about this, that the net force in this case, F net, will be equal to mass times r dot dot. I will designate with 2 dots the traditional time derivative in physics. R in this case, instead of delta r, we will basically say that r is the displacement of the oscillating point with respect to the radial direction from a point where the point mass is in a state of stable equilibrium or does not move, and deviation from that point along the corresponding radius of the circumcenter of the circumcircle of the corresponding parent equilateral triangle is how we keep track of motion. We describe it in terms of some material that we can act on. If you do not like R, use X or any other letter, it doesn't really matter. I personally prefer R because it reflects the fact that the motion is radial along a radius of the circumcircle of the parent regular polygon or an equilateral triangle, and this will be precisely minus K prime R. In this case, this is the equation. If we divide both sides of this equation by m is not 0, and move, for example, this term over here, again, it depends. In different courses, different teachers in different countries do different things, and they may prefer one shape to another. It doesn't really matter. But in one way, we can leave this equation like so. R dot dot is equal to minus K prime over M R. In some other textbooks, probably you will see something like R dot dot plus. Here it will be plus K prime over M R equal to 0. And if we designate precisely this guy omega squared 0 as k prime over m, then in terms of real numbers, this quantity is always greater than 0 in this case to have a meaningful problem. So we can take the square root of both sides and arrive at this expression over here. So once we understand all this, we write down these equations. We do not really have to solve these equations. That's actually maybe another interesting thing about this problem, that we do not really have to solve these equations. Maybe at some point, if you guys are interested, I'll put together an episode that will explain how to solve this differential equation. We can use, for example, just to spice or generate your curiosity. I'll show how Leibniz suggested to do it. Separation of variables and manipulation of differentials is quite straightforward. But here, amazingly enough, we do not really have to solve this differential equation. We simply take this to be the square of the quantity to which we refer as the cyclic frequency of oscillation of the system, of our system, as a whole. So what would the expression be? Now that you guys understand this material, you can write it down. I will erase this. This is basic Newton's second law of motion. That is why this is a solution based on the Newtonian formalism. Then if I erase this, and if we use this formula shown over here, this is a known result. This is another manifestation of mathematical equivalence. Once we reduced the equation of motion of a given system to a shape that is known to us from the previous cases, boom, voila, game over, we have our result. So what do we have? In this case, in general, the cyclic frequency of oscillation of the system of a whole, simple harmonic oscillation, will be what? 2 times the cosine of n minus 2 over 2n pi square root of k over m. This is our general result. K is given, m is given, n is known. This is the general case for a regular, non-degenerate regular polygon on n evidently greater than 2 vertices. And in our case, what is n? Well, n is known. N is equal to 3. And if we put n equal to 3 into both of our formulas that we deduced for the constant of a virtual spring, which I will discuss in a second, shown over here, and n equal to 3 into the expression for the cyclic frequency of the simple harmonic oscillation of our system as a whole, then we will obtain the following results. Now, under n equal to 3, what we will have? K prime, when n is equal to 3, we will have 4 times the cosine of squared of 3 minus 2 divided by 2 times 3 scaled by pi k. And what is that? That is 4 times the cosine squared of, let's do this, 3 minus 2 is 1. 1 over 2 times 3 is 6, pi over 6. Cosine square of pi over 6 is what it will be. Cosine squared of pi over 6 times k, it will be 4 times, let's write it this way, square root of 3 over 2 squared k. Then what do I have? 2 squared is 4. 4 and 4 cancel each other out. Square root of 3 squared is 3. So this will be 3k. So the constant of the virtual spring that connects each oscillating point with the circumcenter of the parent equilateral triangle will be given by 3k. See, this is the guy. And if we conduct the same experiment with the cyclic frequency and evaluate it at n equal 3, what will we have? We will have omega 0 is equal to 2 times, we already know what the deal is, 2 times square root of 3, 2 times square root of 3 over 2. What is this? Well, this is the cosine of pi over 6 times square root of k over m. 2 and 2 cancel each other out. Square root of 3 can be moved in. And now, and here, we have it 3k over m is the cyclic frequency omega 0 when n is equal to 3. This is technically the answer that we were shooting for, square root of 3k over m. This is the cyclic frequency, and that is also one of the reasons why I presented the material that covers the dedicated study of mathematical equivalence ahead of time. That was studied earlier, and now we will see this idea of mathematical equivalence literally all over physics and in many places in mathematics too. So here, amazingly enough, what we managed to prove is the following. The given system that is connected with physical ideal springs, the constant of each of which is k, as shown over here, k, 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 m, 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 is mathematically equivalent. And what is mathematically equivalent? Well, because remember, for the net force, we established that the net force can be represented as k prime times r for the absolute value, of course, and k prime is given over here. This was the expression for the net force, and taking this expression and representing it as k prime exactly gave us the required mathematical equivalence. So our physical system of a triangular spring oscillator is equivalent to what? To, if you will, a virtual system which is comprised also of the same 3 point masses, m, m, and m. The masses this time percolated from the physical original problem into its virtual equivalent, mathematical equivalent, as is intact. But now what we have is 3 virtual ideal springs that connect each point mass with the circumcenter or with the center of the parent regular polygon on n vertices, or in this case of an equilateral triangle shown here this way, and this way. And each such spring oscillates with the frequency, with the cyclic frequency omega 0, omega 0, omega 0. Its value is captured in terms of the locally available material here, square root of 3k over m. And again, this all 3 point masses execute this equivalent simple harmonic oscillation. The system oscillates, executes small amplitude oscillations. This is, of course, we understand this is the so-called Hooke's law. This idea was basically discovered experimentally by the English physicist back in the day. I think his name was Robert Hooke. And for the absolute value, this is, of course, an approximation. And also, there is another detail in the whole works. I did not discuss it with you guys explicitly, but we remember that from the previous episodes. What is the computational goal in especially theoretical physics? The computational goal in theoretical physics is to produce an exact solution of an approximate model. And when we create an approximation, we technically state a bunch of initial assumptions known as axioms, or put it the other way, in negative terms, we throw out things that we do not care about in this context. So what do we not care about in this context? Well, in this context, we do not care about the precise mechanics of the spring. This is just an approximation. In reality, with the microscope on the spring, this will not be the case. The shape of the force as a function of the corresponding coordinate will be more complicated. We ignore that. We ignore the fact that the masses over here, m, 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 are in close proximity. And what is going on between these masses? Exactly, the gravitational interaction. Um, Gamma m1, m2 over r squared ignored. We do not really uh, consider the gravitational interaction between the 3-point masses over here. In reality, the springs are actually also not massless. We just another approximation. We take it that the mass of each spring is way, 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 way smaller than the mass of each oscillating point, the small bead or a small ball. But in reality, again, they possess a non-zero mass. They interact with each other gravitationally. They interact gravitationally with the point masses themselves. But if we decide and it is a bad idea to somehow try to mathematically deep dive into this gravitational interaction, it will produce all sorts of headaches and problems and will basically swamp us with mathematics that we may or may not be able to handle. But the thing is, it will not, even if we can handle the underlying mathematics and fight the fight, it will not affect the study of the system in any significant way. It will only obscure actually that study. This is a bad idea. It will not affect it in any meaningful way. At the macro level, ignoring all these things, the gravitational interaction between all the parts, the toy idea for the toy model of an ideal spring, under these conditions, this is what we have. 3k, 3k, 3k is the constant of a virtual spring, each of which is attached to the circumcenter of the parent regular polygon on n vertices of an equilateral triangle. In this case, on one side, on the other, it is attached to the point mass. Each of these point masses executes, as I showed over here in green, here, here, and here, this radial motion, and all three of these points oscillate in exactly the same way, and the cyclic frequency of this oscillation is precisely captured over here. And now we will cover two more solutions of this problem. These solutions will be much more quicker because the underlying mathematics will be slightly more advanced. But the idea is that, look at this before we deep dive into the solution of this problem that is based on the law of conservation of mechanical energy and the Euler and the Lagrangian equations. Precisely one oscillating point is enough to be a faithful representative for the entire system. That means if we can study the motion of one oscillating point, we know the behavior of the system in its entirety. Now that we solved this problem using the Newtonian formalism and looking at actual forces that generate the motion in a given system is always interesting and fun, even though sometimes the corresponding vector diagrams come out to be quite hairy and next to incomprehensible. But we think that by understanding which forces act which way, working on the vector sum, this and that, we think that we understand how the system evolves over time. But this is not the only way to study the behavior of systems. In higher physics, especially in theoretical physics, for example, the Lagrangian formalism operates solely in terms of energies, kinetic and potential energy. And in this case, because there is no friction in our system, the law of conservation of total mechanical energy does apply. And here, a small wrinkle for those of our viewers who studied even the behavior of a simple harmonic oscillator. They may remember from the theoretical part that the individual types of energy, kinetic and separately potential energy associated with the spring, the proverbial kx squared over 2, does not conserve. These energies do not conserve, but in total, in sum, they change in such a way that when one energy decrements or decreases, the other one increases in such a perfectly calibrated way that in sum, The sum total of these two energies remains constant over time under the conditions specified if that law of conservation of energy applies. So in this case, what can we say about the, let's say we designate with r, let's say this will be our r, the distance r, and this will be our distance x. What can we say about the kinetic energy of one oscillating point? Well, it will be mr dot squared over 2, and we have 3 copies of it, 3, but one representative is enough to give a faithful and complete description of how the system behaves as a whole. Plus, we will have also, let's say, 3 copies of k. Soon it will be over 2, but here it will be this displacement plus this displacement squared. And what do we say about this displacement? Well, there are 2 copies of it, right? One over here and one over here. So that displacement, let's call it delta x. Delta x will be expressible in terms of r, which way? And we remember that angle we already computed. I'm not going to go through all the mechanics again. You guys remember how it's done. It will be 2 times r times cosine of pi over 6. That will be 2 times r times square root of 3 over 2. So this will be r square root of 3. So this r square root of 3 goes over here. And that energy, the total energy, remains constant over time. And if it's constant over time, then the first time derivative of this energy, dE over dt, must be 0 in this case. So if we differentiate this, the left-hand side of this equal sign over time once, what will we have? We will have 3 times m times r dot times r dot second derivative. This is the derivative, the first derivative of a very straightforward function. 2 comes down, cancels out. We get the quantity itself times the first derivative of the quantity, the second derivative, plus 3 times, here again 2 comes down, 3 becomes, square root of 3 becomes 3, and we have what? We'll have 3 times k times r dot. And all these things, because this is a constant, must be equal to 0. Now, 3 is not 0, cancel. That is why, in some sense, we didn't really have to multiply by 3. One representative is a faithful way to describe the behavior of the entire system. And what can we do? Well, we see that the velocity of the oscillating point is a common factor, so we can rewrite it which way? R dot times m times r second derivative plus 3k times r, and this is equal to 0. And now this is back to middle school algebra. What do we have? We have a product of 2, in this case real numbers. It is 0. So what are the possibilities? Both factors could be 0. One factor is 0, the other one is not, and this factor is 0, the other one is not. The r dot, the first time derivative of r, the first time derivative of the oscillating point in the radial direction over here, in general, it is not 0. So when it is not 0, so if r dot is not 0, then what is the only choice? Well, mr dot plus 3k r must be 0. M is not 0. We divide this equation through by 1 copy of m and obtain 3k over mr equal to 0. And this guy precisely over here is our square of the cyclic frequency of the system that oscillates. So here again, the sought after cyclic frequency is given by square root of 3k over m. This is exactly the same result as we obtained earlier, but this time we deduced the same result based on the law of conservation of total mechanical energy. And these computations were in some sense more straightforward. They were perhaps less involved, but you had to know how to differentiate this equation that captures the law of conservation of total mechanical energy. And this is obviously a higher requirement in terms of mathematics, but if you can handle it, then this is a way to do it. And now finally, again, this next segment will be very short because we will pretty much reuse this idea. Remember the expression for the just in case, I'm not sure how well our viewers familiar with the potential energy of an ideal spring. You remember that expression, kx squared over 2, where the x is the displacement of the oscillating point from the neutral position, from the position of stable equilibrium. And this is precisely what it is. This is this guy. So this is, let's say, this is the potential energy, and this right here is the T, or designation for kinetic energy. In some text you will see it as uppercase K. In my time it was uppercase T. Kinetic energy, potential energy, it is a constant. First derivative of the constant is 0. We take the derivatives, carefully analyze the cases, reduce the result to an equation of motion, recognize that this is a previously solved problem. See, mathematical equivalence makes its encore appearance one more time. This is omega 0 squared, and this is the result. And now let's take a look at how this problem can be solved using the Lagrangian formalism. As we approach the solution of the physics problem S3P1 from the Lagrangian formalism standpoint, we will basically hijack in a good way the results that we developed in the previous segments. I will not be dwelling on all the details. I just want to make sure that maybe some viewers in our audience have the question of where, when we constructed the result that I had over here, that delta x is equals to 2 times r times the cosine of pi over 6. Where did this 2 come from? Well, don't forget that once we displace our system, all 3 points from their uh, uh, states of stable equilibrium, there will be 2 x's over here, one on one side and one on the other. So here the total, remember the lambda and lambda from our previous segments, there are 2 contributions from each uh, extremity of the spring. That is why we have 2 cosine square root of 3 over 2. 2 and 2 cancel out. R square root of 3 percolates to the top, and that is where this 2 comes from, just to make sure that everyone is on the same page. Now, from the Lagrangian formalism, we have the Lagrangian will be equal to difference between the kinetic energy and the potential energy. And in this case, it will be what? The kinetic energy is, let's say, 3 copies of mr dot squared over 2 minus, here is minus, don't forget, 3 times k times what? 3r squared over 2. And now again, the law of conservation of total mechanical energy applies. There is no friction. This is an idealization. So the number, how many numbers do we need in order to completely describe the simple harmonic oscillation of 1 point? One number, and we call that generalized coordinates r. coordinate r. If you want to call it something else, z, y, whatever, x, be my guest, it doesn't really matter. So the system from the standpoint of one oscillating mass has only 1 degree of freedom, so n Euler Lagrangian equations decay into just one. And what does this equation say? It says that dl over dt of dl partial derivative with respect to the generalized velocity is equal to partial derivative of L with respect to the generalized coordinate dr, and this is it, game over. So let's do this carefully. dl, the partial derivative of our Lagrangian with respect to the coordinate r, this coordinate over here, the radial displacement of the oscillating point mass is what? This is 0. We treat this as a constant. And what is over here with respect to r? So that will be r times 2. 2 and 2, 2 in the numerator and 2 in the denominator cancel out. So that will be minus 3 times 3k r times that's it. This is it. This is the partial derivative with respect to r. So this is very straightforward. And what is the partial derivative of our Lagrangian with respect to the generalized velocity dr dot? So in this case, we treat this as a constant. It's gone. The derivative is gone. And what do we have here? Well, here we have 3 times m times r dot. Would you agree? 2 in the power goes into the numerator, 2 in the numerator and denominator cancel each other out, 3mr dot. This is it. And then the first derivative of this over time, d over dt of the partial derivative of the Lagrangian with respect to the generalized velocity will be the first derivative of this. The mass remains constant at all times. The first derivative of this bad boy is just basically the second derivative, 3mr dot dot, and by the Euler-Lagrangian equation, this must be equal to this guy. So this will be 3 times k times r. Again, 3 and 3 cancel out, and we have minus over here. Yes, cannot forget the minus. We have our minus just to make sure. mr dot dot is equal to minus 3kr, and we have our equation of motion. Again, divide both sides of this equation by non-zero mass, carry, for example, this term from the right hand side to the left hand side, and obtain the same equation, r dot dot plus 3k over mr is equal to 0. This is even faster. This is way more straightforward. And what is this? This is the square of the cyclic frequency. This is omega 0 squared, and there we have it. The omega itself, let's be careful and write it down. Omega 0 equals square root of 3k over m. Again, exactly the same result as we obtained earlier, but we obtained it through higher brow physics. But when we compare this to the solution that was based on the Newtonian formalism, it may not be as evident from here, from this solution, that this system is equivalent to this. When we worked with forces, when we stepped, into the ring with the forces up close and personal, we were able to see that, yes, mathematical equivalence was basically staring us in the face, and we think that we understood the physics of the underlying process deeper by looking precisely at which forces act away, what is the net force, what is the resultant motion. But this is in some sense, maybe a drawback of the Lagrangian formalism, because it trades the speed and mechanicity, if you will, of the deduction of the equation of motion for the perhaps deeper forces-based understanding of the underlying phenomenon. And in this episode, we looked at all three ways: middle school, high school, and maybe your second or third year in college. Again, I want to stress one more time that we do not really need to solve this equation. All we need to do is reduce the given problem to that equation. That equation is known: simple harmonic oscillator. 3k is, in this case, evidently the constant of the virtual string. And by looking at the mechanics of this here thing, we actually may come out to the arrive at the idea that even from the Lagrangian formalism standpoint, we may realize that our physical system is equivalent mathematically to the system shown over here with the virtual springs, each of which virtual ideal springs, each of which has the same spring constant, 3k. The frequency oscillation is evidently one and the same. In all three different ways, we obtain one and the same result. Now we are done with this problem. If you guys have any questions, use the comment section. If you have any other way to solve this problem, be my guest, share your ideas with the community. It will only enrich our understanding of the problem. But for now, this is it for the physics problem S3P01, and we will move on to a new challenge next. The objective of the next challenge, this will be our first computer science problem of the third season, S3CS1. Remember, with CS we designate the problems in computer science. With the letter P we designate the problems in physics. With the letter N we designate the problems in mathematics. This will be a problem in computer science. This is what usually given in some texts on computer science, on the study of algorithms. And the objective of this problem is to be creative. This is the emphasis. It is possible to sort three integers in any which way. Yes, there is not much intellectual challenge behind this task, but the emphasis in this problem is to be creative. So creatively sort three integers, for example, named ABC, in the ascending order in such a way that on the input into your algorithm, these integers can be in any which order, but on the output, we want to see these integers printed in the way so that the next integer is not smaller than the previous one. 1 should be less than or equal to 2, less than or equal to 3. We want to hear your ideas. Again, even if your implementation, for example, I will share my implementation with you guys using the best programming language of all times, C. My solution will be in C, but yours can be in any pseudo language. It doesn't really matter, maybe something C-like. And whatever your solution is, we want to be your motivation, the story behind how you came up with that sorting algorithm should be creative. The emphasis again on being creative. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you my solution of the computer science problem S3CS1.